A galaxy full of billions of stars existed when the universe was only 300 million years old. Our best models say that should take billions of years. Webb found it in 300 million. We are going to travel through what this galaxy is, why physicists went silent when they saw the data, how it connects to a crack already forming in cosmology, and what it means if more of them keep appearing. If you enjoy space content that actually challenges what we know, subscribe. You will want to be here for what comes next. Brace yourselves. We begin. A single image came back from the James Webb Space Telescope, and the scientists reading it went quiet. The image showed a galaxy, bright, structured, packed with stars. That alone would be remarkable. But the number attached to it was what made people put down their coffee and stare at the screen. The light captured in that image had been traveling for over 13 billion years. When that light first left its source, the universe was only about 300 million years old. To put that in perspective, the universe today is roughly 13.8 billion years old. 300 million years into its life, it was a violent, chaotic fog of gas and radiation. Galaxies were supposed to be embryos at that stage, thin hazes of hydrogen slowly pulling together under gravity, the kind of thing you would need billions more years to turn into something real. This galaxy was already real, fully formed, blazing with the light of billions of stars. The team that found it did not announce it immediately. They ran the numbers again, then again. They checked the instruments. They reviewed the calibration data. Scientists are trained to distrust results that excite them, because excitement is exactly when errors slip through. But every check came back the same. The galaxy was there. The age was real. When the paper finally came out, other researchers read it the way you read something you half expect to be a mistake. They looked for the error. They wanted to find the flaw that would make this comfortable again. Some thought the redshift measurement, the tool used to calculate distance and age in space, might be off. A few proposed that the light could be contaminated by something closer, but the James Webb Space Telescope's instruments are among the most precise tools humanity has ever built. The margins of error here were thin, uncomfortably thin. Redshift works like this. When a light source moves away from you, its light waves stretch out, shifting toward the red end of the spectrum. The farther away something is, the faster the universe is carrying it from us, and the more stretched that light becomes. By measuring exactly how red the light from this galaxy was, scientists could calculate how far the light had traveled, and therefore how long ago it was emitted. The redshift value for this galaxy was extreme, the kind of number that, when you type it into the equation, spits out an age that makes the room feel smaller, 300 million years. In a universe that cosmologists had mapped carefully, with rules about when structure could and could not form, 300 million years was supposed to be empty, quiet, a time before galaxies. And here was one, bright enough to be seen from across the observable universe, across 13 billion light-years of space, sitting in Webb's data, like a challenge. One of the researchers on the team later described the moment of confirmation as deeply uncomfortable. The word they used was not exciting. The word was unsettling. That feeling had a reason. A confirmed galaxy at this age did not just add a new data point to the existing model of the universe. It punched a hole in the model's timeline. And the timeline, as we are about to see, is the backbone of everything we thought we knew about how the universe was built, because the age alone was only the first problem. The second problem was what was inside it. Before we can understand why this galaxy broke something, we need to understand the tool that revealed its age. Redshift is the ruler scientists use to measure the universe. And it works because the universe is expanding. Picture yourself standing on a street corner. A car drives toward you playing music. The sound waves compress as the car approaches, making the pitch higher. As the car passes and moves away, those waves stretch out, and the pitch drops. This is the Doppler effect. Light does the same thing. When a source of light moves away from you, its waves stretch. Stretched light waves shift toward red. The faster something moves away, the redder its light becomes. Now scale this up to the entire universe. Every galaxy is moving away from every other galaxy as space itself expands. The farther a galaxy is from us, the faster it appears to be receding, because there is more expanding space between us and it. This means the most distant galaxies show the most extreme redshift. Their light is stretched so dramatically that it shifts out of the visible spectrum entirely into infrared light. That infrared shift is exactly why the James Webb Space Telescope was built the way it was. Hubble could see visible light beautifully, but the oldest galaxies in the universe had their light pushed far beyond what Hubble's mirrors could detect. Webb was built to see in infrared. Webb was built specifically to see these galaxies. When scientists measured the redshift of this ancient galaxy, they got a value that placed it at a distance corresponding to a time when the universe was roughly 300 million years old. This kind of measurement has a small margin of uncertainty, but scientists cross-check it using spectroscopy, breaking the light apart into its individual wavelengths and analyzing the chemical fingerprints left by specific elements. Those fingerprints appear at known wavelengths in a lab. When they appear shifted in a galaxy's light, the amount of shift confirms the redshift value. The two methods agreed. The galaxy was as old as the first measurement said. Here is why this matters beyond just one galaxy. The age of the universe was not a number scientists guessed. It was calculated through decades of observations, measurements of the cosmic microwave background radiation, which is the faint afterglow of the Big Bang still detectable today, and the observed rate of the universe's expansion. Those measurements produced a timeline, a detailed map of what the universe looked like at each stage of its life. At 300 million years old, that map shows a universe dominated by dark matter and hydrogen gas, slowly clumping together under gravity. The clumps would eventually collapse into the first stars. Those stars would live, die, and seed the surrounding gas with heavier elements. Then new stars would form from that enriched gas. Repeat that cycle enough times across enough generations of stars, and eventually you get a galaxy. But that process, even under the most optimistic conditions our models allow, takes somewhere between 500 million years at minimum. 300 million years is half that minimum. The galaxy in Webb's data skipped a stage that physics said could not be skipped. Some scientists responded by suggesting the redshift measurement, despite the cross-checks, might still carry hidden errors. Others suggested the galaxy might have formed through an unusual collapse event. A few began reaching for theories that had been set aside years ago, models that predicted faster early structure formation, but were shelved because earlier telescopes found no evidence for them. Webb just gave those shelved models a second life. And the next piece of evidence, sitting inside the galaxy itself, was about to make the case for rewriting the timeline. Even harder to ignore. The age was the first shock. What scientists found inside this galaxy was the second. When astronomers study a galaxy, they do not just count the stars, they analyze the light those stars emit to understand what those stars are made of. Stars are not all the same. The very first stars in the universe, the ones that formed from the pure hydrogen and helium left over from the Big Bang, were enormous, hot, and short-lived. They burned through their fuel fast, exploded as supernovae, and scattered heavier elements into surrounding space. Elements like carbon, oxygen, iron, the stuff that makes planets, the stuff that makes you. The next generation of stars formed from that enriched gas. They were smaller, longer-lived, and carried those heavier elements in their composition. Astronomers call these stellar populations. The first generation is called Population 3. The second generation is Population 2. Our Sun belongs to the third generation, population 1, formed from gas that had already been enriched by 2 previous cycles of stellar life and death. Each generation takes hundreds of millions of years to complete its cycle. Stars live, explode, and seed the next wave. You cannot skip a generation. The heavy elements have to be created somewhere before they show up in the next round of star formation. When scientists analyzed the light from this ancient galaxy, the chemical signatures told a story that did not fit a 300-million-year-old object. The stars inside showed signs of enrichment. Heavier elements, the kind that require at least one prior generation of stars to produce, were already present. That means before this galaxy reached the state Webb captured it in, at least one complete cycle of stellar life and death had already occurred inside it. A full stellar generation inside a galaxy that the universe built in roughly 300 million years. Imagine being handed a tree and told it is only 2 years old, then counting the rings inside and finding 50. Some researchers suggested the enrichment signatures could come from a very unusual first generation of stars, ones that were so massive and so short-lived that they completed their cycle in tens of millions of years, rather than hundreds of millions. This is theoretically possible. Population 3 stars, which have never been directly observed, are believed to have been extremely massive. If they burned fast enough, they might have seeded a second generation quickly. But here is the problem. Even accepting the fastest possible population 3 scenario, the math is incredibly tight. The margin between theoretically possible and violates what we know is razor thin. And the galaxy's overall stellar mass, the total weight of all the stars it contains, pushes the problem further. Assembling that many stars across multiple generations inside 300 million years requires a rate of star formation so intense it exceeds every simulation scientists have run of the early universe. Simulations of the early universe have been refined for decades, tested against every galaxy survey ever done. They produce results that match observations across billions of years of cosmic history. Every galaxy we found before Webb fits somewhere in those simulations. This one does not fit, and it is about to get company. The universe has rules. One of those rules is about speed. Gravity pulls matter together. Stars form inside dense clouds of gas. Those stars cluster into galaxies. That process is not instant. Matter has to collapse, heat up, cool down, fragment, and ignite. Every step has a physical minimum time attached to it, constrained by how fast gravity works, how quickly gas radiates heat, and how dense the initial conditions were. Cosmologists calculated these time limits carefully. They used the known density of matter in the early universe, the known temperature conditions, the known rate at which hydrogen gas can cool and collapse. From those inputs, they built the standard model of structure formation. It tells you how massive a galaxy can get at any given age in the universe. A graph with time on one axis and mass on the other, and a firm ceiling above which no galaxy should exist. This ancient galaxy sits above the ceiling. Its stellar mass is estimated to be in the range of several billion times the mass of our Sun. That is enormous for something so young. Our own Milky Way took roughly 10 billion years to accumulate its mass. At 300 million years old, the universe had not yet had time to build anything close to what Webb photographed. Scientists use the phrase tension with the standard model when a discovery is uncomfortable but could still be explained. They use the phrase challenges the standard model when explanations are strained but possible. When the data on this galaxy spread through the community, some researchers jumped straight to the second phrase. A handful, in private conversations later reported in science journalism, used a third phrase: breaks the standard model. Breaking is a strong word in physics. It means the framework does not just need adjusting. It means a core assumption somewhere is wrong. The speed limit on galaxy formation comes from two core assumptions. First, that dark matter in the early universe was distributed roughly evenly, with only small variations called density fluctuations. Second, that those fluctuations grew at a predictable rate under gravity. If either assumption is wrong, the ceiling changes. If dark matter clumped faster, or if the early fluctuations were larger than expected, galaxies could have grown ahead of schedule. Some researchers proposed exactly that. Maybe the density fluctuations in the early universe were more extreme than the cosmic microwave background radiation suggests. Maybe dark matter has properties we have not measured yet that allowed it to collapse faster in certain regions. These are legitimate scientific proposals. They are supported by some theoretical work, but they require revising parameters that have been trusted for decades, and the data forcing the revision came from a single telescope, running at full power for only a couple of years. What makes this especially hard to dismiss is that Webb did not find one of these galaxies. It found several. Each new discovery pushed the same boundary. Each one pointed to the same conclusion. The early universe was building structure faster than it had any right to. Something in the conditions of that era, something we clearly missed, was accelerating the process. And the deeper Webb looked, the more of these impossible objects it pulled out of the dark. To understand what is being broken, you need to know what was built. The Big Bang Theory is the most tested idea in the history of science. It is supported by multiple independent lines of evidence, each discovered by different teams using different tools across different decades. The cosmic microwave background radiation, the abundance of hydrogen and helium in the universe, the observed expansion of space, the age and distribution of the oldest stars we can see. All of it points to the same origin, a universe that began roughly 13.8 billion years ago in an extraordinarily hot, dense state, and has been expanding and cooling ever since. The timeline that follows the Big Bang is not a guess. It is a detailed sequence of physical events, each governed by known forces and confirmed by observations. In the first second, the universe was a plasma so hot that even protons and neutrons could not hold together. In the first 3 minutes, the temperature dropped enough for protons and neutrons to combine into the first atomic nuclei, hydrogen and helium, in a ratio that matches exactly what we observe in the universe today. This match is one of the strongest confirmations the Big Bang model has. For the next 300,000 years, the universe was opaque. Photons, particles of light, could not travel freely because they constantly collided with the dense plasma. Then the universe cooled enough for electrons to bind to nuclei, forming the first neutral atoms. Space became transparent. Light flooded outward. That ancient light is the cosmic microwave background radiation we still detect today as a faint glow across the entire sky. After that came what cosmologists call the Dark Ages, a period of several 100 million years where the universe was dark, cold, and filled mostly with hydrogen gas. No stars, no galaxies. Gravity was slowly pulling matter into filaments and sheets, the skeleton of what would become the cosmic web. Over hundreds of millions of years, dense pockets within those filaments collapsed inward, heating up, igniting as the first stars. This sequence is elegant. It is consistent. Every observatory we have ever pointed at the sky has found galaxies that fit inside it, until Webb. The galaxy Webb found exists inside the Dark Ages on this timeline, or immediately after them at best. The timeline says that region of cosmic history should contain the faint, fragile seeds of the first structures. It says galaxies like the Milky Way were still hundreds of millions of years away from existing. The galaxy Webb found is massive, bright, and chemically complex. It sits in the timeline the way a skyscraper would sit in a neighborhood of empty lots. Either the lots were not as empty as we thought, or the skyscraper got there through a process we do not understand. Both possibilities require changing something fundamental. And as we are about to see, the community is divided on which fundamental thing needs to change. Because the options on the table range from minor adjustments to a complete overhaul of how the universe began. Scientists are precise about the word impossible. They use it carefully. In everyday language, impossible means something cannot happen under any circumstances. In physics, impossible means something cannot happen under the current model's assumptions. That distinction matters enormously because the history of science is a history of impossibilities becoming discoveries. When astronomers first measured the expansion of the universe and found it was accelerating, that was impossible under the physics of the time. Gravity was supposed to slow expansion down. The discovery forced the invention of a new term, dark energy, a placeholder for something that clearly exists but has never been directly detected or explained. The impossibility did not go away. Scientists built a new framework around it and moved forward. When pulsars were discovered in the 1960s, signals so regular they were initially thought to be alien transmissions. The idea of a dead star spinning hundreds of times per second and emitting a precise beam of radiation was considered physically improbable. Now pulsars are standard textbook content. The galaxy Webb found sits in the same tradition. The word impossible being applied to it does not mean physicists are throwing up their hands. It means they are being honest that their current model produces a prediction and the observation contradicts that prediction, and one of them has to give. The model is the standard cosmological framework, built over 60 years and tested against hundreds of thousands of galaxies. The observation is a single image with data confirming an extraordinary age and mass. In science, a model that has passed thousands of tests carries enormous weight. A single contradicting observation, especially a new one from a new telescope, gets scrutinized intensely before it is allowed to challenge the model. That scrutiny has happened. The results held. So now the discussion has shifted from, is this real, to what does it mean? There are roughly 3 camps in that discussion. The first believes a specific parameter in the standard model is slightly wrong, something about how density fluctuations grew in the early universe, and that a small correction will absorb this galaxy without much disruption. The second believes this galaxy points to a genuinely exotic physical process in the early universe, something like primordial black holes accelerating structure formation that falls outside the standard model but does not overturn it. The third, the smallest but most provocative group, believes this galaxy and others like it are evidence that the timeline itself is wrong, that the universe is older than we calculated. That third camp made international headlines when one of its papers was published. It proposed a universe not 13.8 billion years old, but closer to 26.7 billion years old. The paper used this ancient galaxy as a cornerstone of its argument. The proposal was controversial. Other physicists pushed back, but the debate it triggered revealed something the community had been quiet about for years. There was already a crack in cosmology before Webb arrived, and the ancient galaxy may have just made it wider. Before the James Webb Space Telescope turned on, there was a boundary. Every telescope humanity had ever built, from ground-based observatories to Hubble orbiting above the atmosphere, had looked as deep into space as it could. Deeper space means older light. Older light means looking further back in time, and the deepest those instruments could peer with confidence placed the oldest confirmed galaxies at around 400 to 500 million years after the Big Bang. Those galaxies were already surprising, faint, small, and irregular in shape. They looked nothing like the grand spirals and ellipticals we see nearby. They appeared to be the raw, early sketches of galaxies, not the finished products. They fit the model. They were primitive. They were young. They were where the standard timeline said early galaxies should be, small and just getting started. The Hubble Space Telescope's deepest image, called the Hubble Ultra Deep Field, showed roughly 10,000 galaxies crammed into a patch of sky smaller than a grain of sand, held at arm's length. Some of those galaxies were among the oldest ever seen at the time. Scientists studied them carefully. Their ages, masses, and shapes all pointed in the same direction. The early universe was building structure slowly, just as the model predicted. For 2 decades, that image was the furthest humanity had seen. Those faint smudges in the deep background of the ultra-deep field were the frontier, the oldest things we had ever confirmed. Then Webb launched on Christmas Day of 2021. It took months to cool down, align its mirrors, and calibrate its instruments. Scientists waited. The first images, released in the summer of 2022, were spectacular. Galaxies no instrument had ever resolved clearly came into sharp focus. Scientists began scanning the data methodically, searching for candidates, objects whose light was so redshifted that only Webb's infrared eyes could catch them. They found candidates within weeks. Then the spectroscopic follow-up began, breaking apart the light from those candidates to confirm their redshifts. One by one, the confirmations came in. Some were extraordinary but explainable. Others crossed the line. The galaxy that made headlines pushed past everything Hubble had ever found. It reached back to 300 million years after the Big Bang, 100 to 200 million years earlier than anything previously confirmed. That gap, measured in time, sounds small. Measured in cosmology, it is a chasm. The difference between 400 million years and 300 million years on the cosmic timeline separates a universe that might have started building galaxies early from a universe that had no business building galaxies at all. And Webb found it almost casually, during its early survey work, before it had even completed its first round of deep field observations. If the telescope found this in its opening months, scientists began asking a question that should make you pause. How many more of these are out there, waiting in the deep dark that no instrument before Webb could reach? The answer, based on what came next, was more than anyone expected. The James Webb Space Telescope does something no instrument before it could do at this scale. It sees heat. Everything that exists with a temperature above absolute zero emits radiation. The colder an object, the longer the wavelength of that radiation. Objects near room temperature emit infrared radiation, which is invisible to human eyes but detectable by the right sensors. This is why thermal cameras can find a person in total darkness. The body's heat glows in infrared even when visible light reveals nothing. The early universe does the same thing, on a cosmic scale. When a galaxy is extremely far away, the expansion of the universe stretches its light during the billions of years it spends traveling toward us. A galaxy that originally emitted ultraviolet and visible light, the kind human eyes can detect, has that light stretched so dramatically by cosmic expansion that it arrives at Earth as infrared radiation. The further back in time the galaxy formed, the more its light has been stretched, and the deeper into the infrared it sits by the time it reaches us. Hubble was built primarily to see visible light and some ultraviolet. It had limited infrared capability. The galaxies from the first 400 million years of the universe had their light stretched so far into the infrared that Hubble could only detect their faint outlines at best. To see those galaxies clearly, you needed a telescope designed from the ground up to capture infrared light. Webb's primary mirror is roughly 21 feet across, nearly 3 times the diameter of Hubble's. Its mirror is coated in gold, because gold reflects infrared light more efficiently than any other practical material. The telescope is shielded from the sun, Earth, and Moon by a 5-layer sun shield, the size of a tennis court. All of this keeps Webb's instruments cold enough, below -440 degrees Fahrenheit, to detect the incredibly faint infrared signals coming from the earliest galaxies. Webb orbits not around Earth, but around a gravitational balance point, about 1 million miles from our planet. called the second Lagrange point. From there, with its sunshield always between it and any heat sources, it maintains a stable, frigid operating environment that would be impossible in low Earth orbit. The result is a machine capable of detecting light emitted over 13 billion years ago, light that has been stretched by the universe's expansion into wavelengths invisible to every previous telescope. Webb catches that stretched ancient light and resolves it into detailed images. Features that Hubble saw as single dim pixels, Webb renders as full structures, showing shape, size, and composition. When Webb turned its mirror toward the oldest corners of the observable universe, it did not find blurry hints. It found galaxies, clear ones, massive ones. And the data embedded in their light told a story about the early universe that the people who built Webb had not quite expected. The telescope they launched to confirm the Standard Model's timeline was finding evidence that the timeline might need to be revised. And with each passing month of observations, the evidence kept stacking up in one direction. The galaxy's age was disturbing. Its brightness was a separate problem entirely. When scientists measured how much light this ancient galaxy was putting out, the number was far higher than expected for an object that young. Brightness in astronomy translates directly to energy output. Energy output from a galaxy comes primarily from its stars. More brightness means more stars, or stars that are burning unusually hot and fast, or both. The brightness level observed pointed to a star formation rate that was extraordinary. Star formation rate measures how many stars a galaxy is producing per year. Our Milky Way today forms roughly 1 to 3 new stars per year. A moderately active galaxy in the modern universe might form tens of stars per year. The most extreme star-forming galaxies ever observed, called starburst galaxies, can produce hundreds or even a few thousand stars per year during their most active phases. The ancient galaxy Webb found appeared to be forming stars at a rate that challenged even the starburst category for an object of its age, and the conditions the early universe should have provided. This matters because star formation requires fuel. Fuel means gas. The early universe had plenty of gas, mostly hydrogen, but the rate at which that gas can collapse into stars is governed by physical constraints. Gas clouds must cool before they collapse. Cooling takes time. Magnetic fields and turbulence inside gas clouds resist collapse. Gravity fights against heat. All of these factors impose a ceiling on how fast star formation can proceed. For the galaxy to be as bright as Webb measured, it had to have been forming stars at a pace that pushed against or past that ceiling continuously from its earliest moments. The universe would have had to direct enormous quantities of gas into this galaxy and convert it into stars with an efficiency that our models say is very difficult to achieve. One explanation astronomers proposed involves the conditions unique to the very early universe. At that time, the universe was denser overall. Gas clouds may have been more tightly packed. Cooling could have been faster. The primordial gas, nearly pure hydrogen and helium with no heavy elements to complicate the chemistry, may have collapsed differently from the enriched gas we observe in later galaxies. Some theoretical models allow for extremely rapid star formation under these stripped-down early conditions. Those models had mostly been considered edge cases, interesting but probably not representative of reality. Webb's brightness data pushed them back to the center of the conversation. There is another explanation that scientists have not ruled out. A supermassive black hole at the galaxy's center, actively consuming surrounding material, can produce enormous amounts of light on its own. An active galactic nucleus, a black hole caught in the act of feeding, blazes so brightly it can outshine every star in the host galaxy combined. If the ancient galaxy harbored an active nucleus, some of that extreme brightness may come from the black hole, not purely from star formation, but even with a black hole contributing, the stellar mass of the galaxy remains. The stars are there. They formed, and the timeline of their formation still defies the standard model. The brightness was not an illusion. It was a measurement pointing at a process we have not fully understood. And that process, as the next discovery would show, had left its fingerprints in the chemistry of the stars themselves. Dark matter does not glow. It does not emit light, absorb light, or interact with anything we can directly measure. We know it exists because of what it does to everything around it. It bends light through gravity. It holds galaxies together at speeds that would fling stars apart without an invisible extra mass keeping them in. It shapes the large-scale structure of the universe. And in the early universe, dark matter may have done something that completely changes the timeline we have been working with. The standard model of cosmology treats dark matter as relatively smooth in its early distribution, with small variations called density fluctuations scattered throughout. Those fluctuations are the seeds of structure. Gravity amplifies them over time, pulling surrounding matter toward the denser spots. Eventually, those spots collapse into galaxies. The process is slow because the initial fluctuations are small, just tiny variations in density across an otherwise fairly uniform dark matter field. But what if the fluctuations were not small? What if, in certain regions of the early universe, dark matter was far clumpier than the standard model assumes? A denser dark matter clump would pull in surrounding hydrogen gas faster. Gas that collapses faster forms stars sooner. Stars forming sooner means galaxies assembling earlier. In this scenario, the ancient galaxy Webb found did not break the laws of physics. It formed in a region where dark matter happened to be unusually concentrated, giving it a head start that the standard model's average conditions would never produce. This theory is scientifically legitimate. Dark matter's detailed properties in the early universe are still poorly understood. The cosmic microwave background radiation, our clearest window into the early universe's density patterns, shows fluctuations consistent with the standard model on large scales. But on the small scales relevant to individual galaxy formation, the constraints are weaker. There is room in the data for larger fluctuations than standard models typically include. Some physicists have gone further and proposed a specific kind of dark matter that would have clumped more aggressively in the early universe. Ideas involving dark matter that cooled faster or that had a stronger tendency to collapse into tight structures have been in the theoretical literature for years. They were never ruled out, just not needed, until Webb found something that needed explaining. The acceleration theory, as this line of thinking is sometimes called, has appealed precisely because it does not require changing the Big Bang timeline itself. The universe is still 13.8 billion years old. The Big Bang still happened when we calculated it did. The cosmic expansion still proceeded as measured. Only the behavior of dark matter in the early universe is adjusted. A smaller revision with potentially large consequences. However, a smaller revision with large consequences is still a revision. It still means something we assumed about dark matter was wrong, and it raises a follow-up question that no one has fully answered. If dark matter clumped faster in certain regions, where are the other galaxies that should have formed in those same regions? The ancient galaxy should have neighbors, galaxies that formed around the same time in the same overdense patch of dark matter. Webb has been looking. What it has been finding is enough to push that question from theoretical to urgent, because the ancient galaxy, it turns out, was not alone. Science has a basement, packed into journals, conference proceedings, and the hard drives of theorists who work in relative obscurity. There is a collection of models that were once proposed, tested against available data, and found to be unnecessary. They were not proven wrong. They were just outcompeted by simpler explanations that fit the observations at the time. Science tends to favor the simplest model that explains all the data. When a complicated model and a simple model produce the same predictions, the simple one wins. After Webb's discoveries, some theorists went back to the basement. One category of shelved models involves what is called a running spectral index. This refers to the shape of the distribution of density fluctuations in the early universe. The standard model assumes that fluctuations are distributed across scales in a specific way, described by a smooth, flat spectrum. A running spectral index means that spectrum is tilted, with stronger fluctuations at smaller scales. More power at small scales means more material available for galaxy formation on those scales. Earlier, the standard model spectral index value comes from measurements of the cosmic microwave background radiation. Those measurements fit the data extremely well across the scales that have been measured, but at very small scales below what the background radiation data can clearly resolve, the constraints loosen. A running spectral index with more power at small scales would be invisible to our current measurements of the background radiation, but it would produce exactly the kind of early galaxy formation Webb is now observing. A team revisiting this idea published updated work in 2023 after Webb's first confirmations came in. They showed that a modest adjustment to the spectral index within the observational uncertainties allowed by existing data could reproduce a galaxy like the one Webb found without requiring any other changes to the standard model. The paper was careful and limited in its claims, but it attracted significant attention because it offered a path to absorption, a path where Webb's galaxy breaks nothing fundamental, just reveals a parameter we had assumed was flat when it had a subtle tilt. Other shelved models involve modified gravity. General relativity, Einstein's theory of gravity, has passed every experimental test ever devised. But in the extreme conditions of the early universe, some theorists have proposed that gravity may have behaved with slightly different strength or slightly different characteristics than the equations currently predict. A stronger effective gravity in the early universe would cause matter to collapse faster, building galaxies ahead of schedule. These modified gravity ideas were always controversial. They required changes to physics that have been tested to extraordinary precision in other contexts. But the precision tests were conducted in relatively calm modern conditions. The early universe was neither calm nor modern. The conditions were so extreme that testing the same physics there is genuinely difficult. What Webb did was move these conversations from speculative to urgent. The galaxy in the data was no longer a thought experiment. It was a confirmed object. Every model that might explain it deserved a second look, even the ones that had been sitting in the basement for years, quietly waiting for the observation that would make them relevant again. And while theorists were dusting off old frameworks, the observers kept pushing Webb's mirrors deeper, looking for more. What they found next made the single galaxy problem look manageable by comparison. The first fraction of a second after the Big Bang was the strangest moment in the universe's history. Physics as we understand it today breaks down at that point. The energies involved were so extreme that the four fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, may have been unified into a single force. The universe was not just hot, it was in a state so different from anything that exists today that our equations lose their footing. What most cosmological models agree on is that the universe went through a phase called cosmic inflation. In an incredibly brief window, far shorter than any unit of time you have heard of, the universe expanded at a rate so fast it dwarfs anything measured since. Regions that were in contact with each other were suddenly separated by enormous distances. Space itself stretched at speeds that put even the current expansion to shame. Inflation was proposed to solve several problems with the standard Big Bang model. It explains why the universe looks almost perfectly uniform in every direction, which is puzzling because regions of the universe now separated by billions of light years should never have been in contact long enough to reach the same temperature. Inflation connected those regions early, let them equalize, then separated them during the expansion. It also explains the flatness of the universe's geometry, which observations confirm. Inflation is confirmed in its broad strokes, but the details of how inflation ended are still debated. One controversial but scientifically grounded idea proposes that inflation did not end uniformly everywhere at once. Instead, different regions of the early universe may have exited the inflationary phase at slightly different times or with slightly different energy densities. Regions that exited inflation earlier would have had more time to cool and collapse. Regions that exited with higher energy densities would have had more raw material to work with. In either case, you get pockets of the early universe that were structurally ahead of the average. If the galaxy Webb found existed inside one of those pockets, its impossible formation speed becomes explicable within the framework of known physics. It was formed in a region where inflation's aftermath was favorable, where conditions were denser, cooler, or simply further along than the average universe at that time. This theory does not require new physics. It requires accepting that inflation was messier than the clean, uniform picture most models assume. Theorists who work on inflation have proposed uneven or inhomogeneous inflation models for decades. They were always considered possible but hard to confirm without direct evidence. An ancient, overmassive galaxy sitting in the wrong part of the cosmic timeline could be that evidence. The catch is that this explanation predicts other consequences. If certain regions of the early universe were structurally ahead of schedule, there should be a large-scale pattern to where ancient galaxies cluster. Webb's ongoing surveys should, over time, reveal whether these ancient galaxies are randomly scattered or whether they group together in ways that match the pattern of uneven inflation. That test is ongoing. The data is accumulating, and what it reveals over the next few years will either close one door or open several more. But before that result arrives, something happened that made the single galaxy argument impossible to dismiss as a fluke. One galaxy could be an outlier. Science accepts outliers. A single anomaly, however strange, can sit at the edge of a model without breaking it. Statisticians have terms for this: edge cases, tail events, rare fluctuations. One impossible galaxy, while deeply interesting, allows for the possibility of a measurement error, an unusual formation event, or a cosmic coincidence. Then Webb found a second one. Shortly after the first confirmations came in, astronomers analyzing a different region of Webb's data identified another candidate. The spectroscopic follow-up confirmed it. A second galaxy, similarly ancient, similarly massive, with a redshift placing it in the same forbidden window of cosmic time. Two galaxies, both existing when the universe was under 500 million years old, both with stellar masses that challenge the standard model's upper limits. Two data points do not make a pattern in strict statistical terms. But in cosmology, where you are looking at the entire observable universe and finding the same type of impossible object in two separate and independent observations, the conversation shifts. An outlier can be one, two outliers in the same forbidden zone found by the same telescope during its early survey work push the probability of a systematic error down sharply. They also push the probability of a model problem up. The discovery of the second galaxy drove a different kind of response in the scientific community. The first galaxy produced skepticism and intense scrutiny of the data. The second produced something closer to urgency. Papers began appearing faster. Conferences dedicated specific sessions to early universe galaxy formation. Theorists who had been watching cautiously began publishing their revised models. Something important happened in the framing of the debate as well. Before the second galaxy, the dominant question was whether the first observation was correct. After the second, the dominant question became what physical process produced both of them. That shift, from doubt to investigation, is meaningful. It marks the moment the community moved from defending the standard model to preparing to revise it. It also produced a sharper focus on what the two galaxies had in common. Their ages were similar, their masses were similarly extreme. Their brightness levels both exceeded model predictions. The consistency between them hinted at a population, not two accidents. If there was a population of ancient massive galaxies forming in the early universe at rates our models could not explain, then the early universe itself behaved differently from our reconstruction of it. Scientists began asking how many more existed. They estimated, based on the sky coverage Webb had surveyed so far, what the total number of such galaxies across the full observable universe might be. The estimates were unsettling. They suggested that these galaxies, while rare, were numerous enough to represent a genuine feature of early cosmic history, rather than an exotic accident. And if they represent a genuine feature, the model needs to account for it, not with a footnote, with a fundamental revision to how we describe the universe's earliest chapters. The question now was how deep that revision would need to go, and the answer, hiding in the stars themselves, was deeper than most physicists were comfortable admitting. Results this extraordinary demand extraordinary caution. The team behind the first ancient galaxy's confirmation knew this. Before any paper went public, the data went through a process that most scientific discoveries never require. Standard peer review asks whether the methods are sound and the conclusions supported by the evidence. This analysis went further. The team examined every possible source of error with a level of scrutiny usually reserved for results that directly challenge foundational physics. And this result directly challenged foundational physics. The redshift measurement was checked using two independent methods. Photometric redshift estimates how far light has shifted by comparing brightness across different wavelength filters. Spectroscopic redshift confirms it by analyzing the precise wavelengths of specific chemical signatures. Both methods agreed. The galaxy's light had been traveling for over 13 billion years. The telescope's calibration data was reviewed. The James Webb Space Telescope undergoes continuous calibration monitoring. Its instruments are checked against known reference stars and standard candles, objects whose brightness and properties are reliably known to ensure measurements remain accurate over time. No anomalies appeared in the calibration logs corresponding to the observations in question. Contamination was considered. One concern was whether light from a closer, less remarkable galaxy could have blended with or mimicked the signal of a distant one. Careful analysis of the spatial distribution of the light ruled this out. The signal was clean and consistent with a single, compact, distant source. The possibility of gravitational lensing was examined. Massive objects between us and a distant galaxy can bend and amplify the galaxy's light, making it appear brighter and sometimes distorting its apparent properties. Lensing can cause a galaxy to look more massive or luminous than it actually is. The team checked the field around the galaxy for any intervening mass that could produce significant lensing. The lensing contribution in this case was small, and even accounting for it did not bring the galaxy's properties into the standard model's acceptable range. After all of this, after eliminating every systematic explanation the team could devise, the paper was submitted. Peer reviewers at the journal added their own scrutiny. Questions came back. The team answered them. Revisions were made. The paper was accepted. Publishing a result that breaks the model is a career risk in science. A wrong result, especially one that challenged something as foundational as the Big Bang timeline, would follow the authors permanently. The fact that the team published, despite the risk, after exhausting every alternative explanation they could construct, is itself a signal worth paying attention to. What came next surprised even the skeptics. Instead of a swift rebuttal that dismantled the data, the response was a wave of follow-up papers, some pushing back, some reinforcing, and several proposing theoretical frameworks that accepted the data as real and tried to explain it. The scientific community, slowly and with characteristic caution, began treating the ancient galaxy as a real object that required a real explanation. The data was holding. The model was the thing that had started to wobble. And the wobble, as the next chapter reveals, had a name that physicists had already been quietly discussing for years before Webb ever launched. To understand why the ancient galaxy result is so difficult to dismiss, you need to understand what the James Webb Space Telescope actually is. As a machine, building a telescope to see the first galaxies required solving engineering problems that did not have existing solutions. Every component had to perform at the absolute boundary of what physics allows. The primary mirror is the telescope's eye. Webb's mirror is made of 18 hexagonal segments, each about 4.5 feet across, coated in a thin layer of gold. The segments fold together for launch and deploy in space, aligning with each other to within a millionth of an inch. That alignment is not done once and left. An active system of tiny motors continuously adjusts each segment to maintain the mirror's perfect shape as the telescope's temperature shifts by fractions of a degree. At those scales, even microscopic thermal expansion would blur the images if left uncorrected. The detectors behind the mirror are cooled to temperatures close to absolute zero. Infrared astronomy requires cold instruments because heat produces infrared radiation, and a warm detector would flood itself with its own noise. Webb uses a mechanical cryocooler, essentially a high-precision refrigerator, to keep its mid-infrared instrument at around -447 degrees Fahrenheit, within a few degrees of the coldest temperature anything can reach. At these temperatures, the detectors can pick up single photons, individual particles of light, from objects 13 billion light-years away. A single photon from the ancient galaxy arriving at Webb's mirror after a 13 billion-year journey is registered. This is what allows spectroscopy at cosmic distances. There are so few photons coming from objects that far away and so faint that any detector less sensitive would simply miss them. The telescope's location, 1 million miles from Earth at the second Lagrange point, was chosen because it allows the 5-layer sun shield to block thermal radiation from the Sun, Earth, and Moon simultaneously, keeping the entire cold side of the telescope in permanent shadow. Hubble, in low Earth orbit, passes through Earth's shadow and sunlight every 90 minutes, creating temperature swings that limit observing time and thermal stability. Webb does not have this problem. It sits in a stable thermal environment, always cold, always aligned, always ready. All of this engineering translates directly into data quality. When Webb produces a redshift measurement, the uncertainty attached to that number is smaller than what any previous telescope could achieve for objects at the same distance. When Webb performs spectroscopy on a faint, distant galaxy, the chemical fingerprints it reads are clear enough to identify specific elements, not just vague, broad features, in the spectrum. This precision is why the scientific community took the ancient galaxy results seriously so quickly. A measurement of this kind from an older, less capable telescope would have been treated as preliminary and requiring confirmation. A measurement from Webb carries a different weight. The instrument was designed specifically to make exactly this kind of observation, at exactly these distances, with exactly this level of accuracy. The telescope's precision does not make the result impossible to dispute. Science is always open to revision, but it raises the bar for what a counter-argument needs to achieve. And so far, no counter-argument has cleared that bar. The galaxy's age and brightness were extraordinary. The stars inside it were a different kind of extraordinary. Stars carry their history in their light. Every element a star contains absorbs light at specific wavelengths, leaving dark lines in the spectrum of light that star emits. These lines are fingerprints. Iron absorbs light differently from carbon. Oxygen absorbs at different wavelengths from silicon. By reading those fingerprints in a galaxy's combined light, Astronomers can determine what elements the stars inside it are made of and in what proportions. In the very early universe, the chemical composition of stars should be simple. The Big Bang produced hydrogen, helium, and trace amounts of lithium. That is almost the entire menu. No carbon, no oxygen, no iron. Those heavier elements are manufactured inside stars through nuclear fusion and scattered into space when stars die. The first stars in the universe, forming from pure primordial gas, should contain almost none of those heavier elements. When astronomers analyzed the ancient galaxy Webb found, the spectral fingerprints showed heavier elements that require stars to make, elements that require those stars to have lived their full lives, died, and scattered their contents into surrounding gas before the next generation formed from that enriched material. This is the stellar population problem, stated in chemical terms. The presence of heavy elements is direct evidence that at least one previous generation of stars had already completed its full life cycle inside this galaxy. And that generation had to have formed, burned, and died before the light Webb captured was emitted, all within a timeline of 300 million years. Stellar evolution has minimum timescales. The most massive stars, which produce the heaviest elements in the largest quantities, live for only a few million years. This sounds fast. On the scale of cosmic history, it is fast, but for a generation of stars to enrich surrounding gas sufficiently to leave clear spectroscopic signatures in the next generation, you still need time for the cycle to complete. For lower mass stars, which contribute different elements in different proportions, lifetimes extend to tens or hundreds of millions of years. Modeling the chemical composition of a galaxy requires working backward through its history, identifying which types of stars produce the observed element ratios, how long those stars lived, and how much time had passed since they died. The models applied to this ancient galaxy produced a history that, even under the most generous assumptions about fast stellar evolution, required more time than the age of the galaxy should allow. Some researchers proposed that the first generation of stars, the elusive population 3 stars that formed from pure primordial gas and have never been directly detected, may have been so massive and so short-lived that they completed their cycle in only a few million years, seeding the next generation with sufficient metals for the chemical signatures Webb observed. This is theoretically possible. Population 3 stars are believed to have been extraordinarily massive, but even this explanation strains the timeline. A few million years for a first generation, plus the formation time of the second generation, plus the time needed for the second generation's stellar evolution to produce the observed chemical signatures. Stack those timescales inside 300 million years, and the window becomes extremely narrow. The chemical evidence did not just confirm the galaxy's impossibility, it deepened it, and it pointed towards something even more unsettling, an idea about whether the universe's age itself might be wrong. The lambda CDM model is the closest thing cosmology has to a unified theory of the universe. Lambda stands for the cosmological constant, the term Einstein added to his equations to represent what we now call dark energy, the force driving the accelerating expansion of the universe. CDM stands for cold dark matter, the invisible slow-moving matter that makes up roughly 27% of the universe's total energy content. Together, these two components, alongside ordinary matter, radiation, and the Big Bang's initial conditions, define the standard model of cosmology. The lambda CDM model has been tested against an enormous range of observations. The cosmic microwave background radiation, the large-scale distribution of galaxies across billions of light years, the abundance of light elements like hydrogen and helium created in the first 3 minutes after the Big Bang, the history of cosmic expansion measured through distant supernovae, the clustering patterns of galaxies across the universe's history. Every major independent line of evidence has returned a result consistent with this framework. No model in the history of science has passed more diverse tests. Cosmologists built it over 60 years, absorbing every contradicting observation, refining parameters, adding components where necessary. It became the bedrock of the field. And yet, it was already showing a crack before Webb launched. The crack is called the Hubble tension. It comes from a measurement that the model needs to be internally consistent. The current rate of the universe's expansion, called the Hubble constant. This number can be measured two ways. You can calculate it from the cosmic microwave background radiation, using the early universe's physics to predict what the expansion rate should be today. Or you can measure it directly from nearby galaxies and supernovae, using the current universe's properties. For decades, cosmologists assumed these two measurements would agree. They do not. The early universe calculation produces a slightly lower number. The direct measurement produces a slightly higher number. The gap between them is small in absolute terms, but it is statistically significant enough that it cannot be explained by measurement error alone. Something in the model, or something in the physics, is off. Cosmologists have been arguing about the Hubble tension for years. Proposals range from subtle errors in how distances to nearby galaxies are calibrated, to genuine new physics involving dark energy changing in strength over cosmic time, to additional unknown particle species affecting the early universe's expansion. When Webb found the ancient galaxy, researchers working on the Hubble tension noticed something. An ancient, unexpectedly massive galaxy existing far earlier than the model allows could be a symptom of the same underlying problem, driving the Hubble tension. If the expansion history of the universe is slightly different from what lambda CDM assumes, specifically if the universe expanded more slowly in its early stages, structure would have had more time to form. A slower early expansion fits a universe that appears older than its calculated age. A universe that appears older than its calculated age has room for galaxies that built themselves earlier than the current timeline allows. This connection made the ancient galaxy more than an isolated curiosity. It became a potential piece of a puzzle that cosmologists had been failing to solve for years. And it raised the question that one research team decided to pursue directly. What if the universe's calculated age is simply wrong? That question, and the paper that tried to answer it, shook the field in ways that are still being debated today. Revising the lambda CDM model is not a small undertaking. The framework is embedded in every major cosmological simulation, every galaxy survey analysis, every calculation astronomers use to interpret observations of the distant universe. Changing a core parameter does not just update a number in a textbook. It cascades through decades of published work, recalibrating conclusions that were built on the previous value. It means revisiting surveys, reanalyzing data, and in some cases, overturning results that shaped careers and defined entire subfields. This is why cosmologists do not propose revisions lightly, and it is why the scientific community's response to Webb's ancient galaxies carried a particular weight. Researchers who had spent their careers building on lambda CDM's foundation were now being asked to consider whether that foundation had a flaw baked into it from the beginning. The specific challenge came from the model's treatment of early universe conditions. Lambda CDM describes how matter, both ordinary and dark, was distributed at the moment the universe became transparent, roughly 300,000 years after the Big Bang. From that starting point, it calculates how structure grew over time. The inputs come from precise measurements of the cosmic microwave background radiation, the faint afterglow of that transparency moment, which satellites have mapped in extraordinary detail. Those measurements are good, extraordinarily good. The cosmic microwave background data is among the most precise in all of science. The temperature variations across the sky, fluctuations of only 100,000th of a degree, have been mapped at resolutions that reveal structure down to fractions of a degree. across the sky. The Lambda CDM model fits those variations with remarkable accuracy. The problem is that fitting the early universe snapshot perfectly does not guarantee that the model correctly predicts everything that follows. The snapshot captures conditions at one specific moment. The model then extrapolates forward across 13 billion years of cosmic history, using equations that assume dark matter behaves a certain way, that dark energy has a constant strength, and that the initial fluctuations in density follow a specific mathematical distribution. Each of those assumptions is reasonable, each is supported by evidence, but each is also an assumption, not a proven law, and each introduces a potential error that compounds over 13 billion years of extrapolation. The ancient galaxies Webb found exist at the far end of that extrapolation, in the era most distant from our present observations and most sensitive to errors in the initial conditions. If any of the model's assumptions carry a subtle flaw, the early universe is exactly where that flaw would show up most dramatically. Some researchers proposed adjusting the model's treatment of how density fluctuations grow. Others focused on dark matter's properties in the high-density early universe. A smaller group questioned whether dark energy was truly constant, suggesting it may have been stronger or weaker in the past, affecting the expansion history in ways that would shift the timeline for galaxy formation. Every proposal had merit. Every proposal also had costs, requiring changes to other parameters that would need to be reconciled with existing observations. The scientific community was not facing one clear path forward. It was facing a map with multiple routes, no obvious best choice, and the certain knowledge that at least one route leads somewhere significantly different from where cosmology currently stands. The deeper the investigation went, the more apparent it became that the ancient galaxy was pulling on a thread connected to far more than one discovery. And somewhere along that thread was an idea so radical that most physicists initially refused to take it seriously. The cosmic microwave background radiation is the oldest light in the universe. It was released 300,000 years after the Big Bang, when the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms. Before that moment, the universe was an opaque plasma. Photons could not travel freely. The instant the plasma cleared, light flooded outward in every direction. That light has been traveling ever since, cooling as the universe expanded, fading from the intense glow of a hot plasma to a faint microwave hiss, detectable today at a temperature barely above absolute zero. Satellites have mapped this radiation across the entire sky. The maps show a near-perfect uniformity, with tiny variations that carry the imprints of the early universe's density fluctuations. Those fluctuations grew over time into the large-scale structure of galaxies and galaxy clusters we see today. The maps are so detailed and so consistent with the Lambda CDM model that for years they were treated as confirmation the model had captured the early universe's conditions correctly. Scientists called these conditions the initial conditions of the universe. They include the temperature distribution, the density fluctuations, the balance between matter and radiation, and the geometry of space. Lambda CDM was calibrated to these initial conditions. The model then runs forward in time, predicting how those conditions evolve into the universe we observe today. The ancient galaxy sits inside the region of cosmic history just after those initial conditions were set. If the galaxy looks wrong relative to the model, one possibility is that the model's prediction is off. Another possibility is that the initial conditions themselves were different from what the cosmic microwave background measurements suggest. This is a deeply uncomfortable idea. The cosmic microwave background measurements have been made by multiple independent satellites, cross-checked exhaustively, and agreed upon by teams with no coordination between them. Suggesting the initial conditions are wrong means suggesting that those measurements carry a systematic error that every independent team missed. Some researchers have proposed a version of this that does not require the measurements to be wrong, but rather the interpretation to be incomplete. The cosmic microwave background captures conditions at 300,000 years after the Big Bang. The period before that, from the Big Bang itself to the 300,000-year mark, is not directly observable. Our picture of those earliest moments comes from theoretical physics, from models of inflation, particle physics, and thermodynamics extrapolated backward from what we can see. If something in that earlier, unobservable period was different from our theoretical models, the initial conditions at 300,000 years could look exactly as measured and still be the product of a history we have wrong. The measurements would be accurate. The history behind them would be incomplete. This interpretation opens space for early galaxies to exist without requiring the cosmic microwave background data to be flawed. It places the unknown in the period before the universe became transparent, a period where theoretical models are our only guide and where confirmation is extremely difficult. Pinning down what was different in those first 300,000 years requires either a theoretical breakthrough or an observational window into that era. Gravitational waves from the very early universe, which some next-generation detectors may be able to detect, could eventually provide such a window. Until then, the gap in our knowledge is real. And into that gap, one team of researchers stepped with a proposal that reframed the entire conversation. In 2023, a paper appeared that divided the cosmological community almost immediately. The author, Rajendra Gupta, a physicist at the University of Ottawa, proposed that the universe is approximately 26.7 billion years old, nearly twice the currently accepted figure of 13.8 billion years. The ancient galaxy Webb found was one of the central pieces of evidence cited in the paper. If the universe is twice as old, its timeline has room for the ancient galaxy's stellar populations, its chemical enrichment, and its extraordinary mass. An extra 13 billion years resolves every contradiction by giving the universe the time the standard model insists it does not have. The proposal was not a casual suggestion. Gupta developed it by combining two theoretical frameworks that had previously existed separately. The first involves what is called tired light, a hypothesis originally proposed in the 1920s that suggests photons lose energy as they travel through space, which would cause their light to redshift without requiring the source to be moving away. The standard model rejects tired light because it makes predictions that conflict with multiple observations, including the way supernovae age and how the cosmic microwave background radiation looks. Gupta proposed a modified version of tired light that attempts to sidestep some of those objections. The second framework involves the possibility that fundamental physical constants, values like the speed of light or the strength of electromagnetic interactions, may have changed over cosmic time. Constants are called constants because every measurement ever made confirms they are stable. Suggesting they change is a significant departure from established physics. The response from the mainstream cosmological community was largely skeptical. Several physicists published critiques pointing out that tired light, even in modified forms, struggles to reproduce the specific patterns observed in supernova light curves and the angular scale of features in the cosmic microwave background. These patterns are precise, well-measured, and tightly constraining. A cosmology that changes the universe's age by a factor of 2 needs to match all of them, not just the galaxy formation timeline. Gupta's paper acknowledged some of these tensions and proposed ways to address them. Critics argued the proposed solutions introduced new problems. The debate produced a substantial number of responses and counter-responses, which is itself significant. Papers that are straightforwardly wrong tend to be ignored. A paper that produces sustained debate, even if ultimately found to be incorrect, is pointing at a real tension in the field. Whether or not the specific proposal holds up, the conversation it started forced a productive clarification. If the universe is not twice as old, What exactly is it about the Standard Model's timeline that accommodates the ancient galaxy? The burden shifted. Defending the Standard timeline now required a positive explanation, not just a dismissal of alternatives. That demand for a positive explanation led researchers directly toward the pre-existing fracture in cosmology, the Hubble tension, which had been quietly undermining confidence in the Standard Model for years before Webb's discoveries arrived to amplify it. There is a number at the center of cosmology called the Hubble constant. It describes how fast the universe is expanding right now, measured in miles per second per megaparsec, which means for every roughly 3.2 million light-years of distance between two objects, they are moving apart by a specific number of miles per second. That number, depending on how you measure it, is either around 44 miles per second per megaparsec or around 47 miles per second per megaparsec. 3 miles per second per megaparsec sounds like a trivial disagreement. In practice, it is a crisis. The two values come from two completely different measurement methods. The first uses the early universe as a laboratory. Scientists take the precise measurements of the cosmic microwave background radiation, feed them into the lambda CDM model, and calculate what the expansion rate should be today based on the universe's known age, composition, and geometry. The answer consistently comes out near 44. The second method uses the present universe directly. Scientists measure distances to nearby galaxies using a chain of calibrated tools, starting with variable stars called Cepheids, whose brightness follows a known pattern that lets astronomers calculate how far away they are, and extending outward using type Ia supernovae, stellar explosions whose peak brightness is reliably consistent. By measuring how fast these calibrated objects are receding, scientists calculate the current expansion rate. That answer consistently comes out near 47. Both methods are among the most carefully checked measurements in science. Multiple independent teams using different calibration approaches have repeated them. The gap stubbornly persists. At the level of statistical certainty involved, the probability that both measurements are correct under the same model is vanishingly small. Something is wrong. Either the early universe measurement carries an error that has survived every cross-check, or the late universe measurement does, or the model connecting the two is flawed. The ancient galaxy Webb found connects to this tension in a specific way. The Hubble constant directly controls the calculated age of the universe. A higher expansion rate produces a younger universe. A lower expansion rate produces an older one. The early universe measurement, which gives the lower Hubble constant value, produces a slightly older universe. The late universe measurement, which gives the higher value, produces a slightly younger one. A universe that expanded more slowly in its early stages, which certain modifications to lambda CDM allow, would be effectively older in terms of the time available for structure to form. More time for structure means more room for early massive galaxies. The Hubble tension and the ancient galaxy problem are potentially symptoms of the same underlying issue. A mismatch between our model of the early universe and what the universe actually did. Several physicists have published models that attempt to resolve the Hubble tension in ways that simultaneously create more room in the timeline for early galaxy formation. None has yet achieved consensus. The solutions tend to fix one measurement while straining another. The problem is tightly interlocked, and pulling on any single thread changes the tension throughout the whole fabric. Webb's discoveries did not create the Hubble tension. They inherited it and amplified it. The ancient galaxy arrived into a cosmological community already quietly aware that its most trusted model had a leak. What Webb did was show that the leak was bigger than previously admitted. The Big Bang theory is not fragile. It is important to understand that clearly before considering what would happen if more ancient galaxies keep appearing. The Big Bang is supported by three independent and essentially irrefutable pillars: the expansion of the universe, which has been measured directly and confirms that everything is moving apart from everything else, pointing backward to a single origin. The cosmic microwave background radiation, the direct light from the universe's early plasma phase, which matches the Big Bang's predictions with extraordinary precision, and the abundance of light elements, hydrogen, helium, and lithium, in the universe, which matches the ratios produced by the Big Bang's nucleosynthesis calculations to multiple decimal places. No single anomalous galaxy, however impossible it appears, touches those pillars. The Big Bang happened. The universe expanded from a hot, dense state roughly 13.8 billion years ago. That conclusion is secure. What is secure? What is less secure is the detailed timeline of what came after. The Big Bang itself, the expansion, the early plasma, the first atomic nuclei, these are confirmed. The model of how the first galaxies formed, when they appeared, how massive they could become and how quickly, these rest on assumptions about dark matter, dark energy, and early universe conditions that are far less directly tested than the Big Bang itself. The distinction matters enormously. A discovery that challenges galaxy formation models does not require the Big Bang to be wrong. It requires the period after the Big Bang, the specific mechanics of how matter organized into structure, to be revised. That is a meaningful and significant revision. It is not the same as discarding the foundation. Scientists sometimes use the phrase, "the Big Bang theory bends before it breaks," to describe the situation. The discovery of dark energy in the late 1990s required adding a new component to the model, a significant revision. The discovery of the Hubble tension required acknowledging a genuine, unexplained discrepancy. Each time, the framework absorbed the challenge by becoming more complex, not by collapsing. Ancient galaxies, if they continue appearing in Webb's data and in the data from future telescopes, will force another round of complexity. The model will grow. Parameters will be adjusted. New physics may need to be incorporated. The result will look different from the current Lambda CDM model in its details, perhaps significantly different. But the universe will still have begun in a hot, dense state. Light elements will still have formed in the first 3 minutes. The cosmic microwave background will still be the afterglow of the plasma phase. These facts are bedrock. What changes is the chapter that follows, the story of how a smooth, hot, expanding gas became the structured cosmos of galaxies, clusters, and filaments we inhabit today. That chapter, it turns out, may have had a beginning more dramatic, more accelerated, and more extraordinary than our models predicted. And the deeper Webb looks, the more evidence accumulates that the early universe was doing something we do not yet fully understand. Ancient galaxies were expected to be messy. The standard model of galaxy formation predicts that the earliest galaxies should look chaotic. In the universe's youth, structures had not had time to settle into ordered forms. Gas was still falling inward from the surrounding cosmic web. Dark matter halos were still assembling through collisions and mergers. Early galaxies, according to the model, should be irregular blobs, clumpy and asymmetric, the raw, disordered products of a universe still in the act of organizing itself. The Hubble Space Telescope's deep field images supported this picture. The most distant, oldest galaxies visible to Hubble looked ragged and irregular. Their shapes were inconsistent, their light distribution patchy. They fit the prediction of chaotic early universe structures exactly. The ancient galaxy Webb found does not look like that. Its structure is surprisingly organized. Astronomers analyzing its morphology found that it displays a disc-like shape, broadly similar in organization to galaxies that, according to the standard model, should not appear until billions of years later. A disk forms when material settles into a rotationally stable configuration. That settling process requires time, multiple gravitational interactions, angular momentum redistribution, and a period of relative quiet in which the galaxy is not being constantly disrupted by mergers and infalling material. For a galaxy 300 million years old to display disk-like organization, the settling process would have had to begin almost immediately after the galaxy formed. There would have been no time for chaotic early dynamics to play out before orderly structure appeared. This is a separate problem from the mass and brightness issues. A galaxy can be too massive too early without also being too structured. The fact that this galaxy challenges the standard model in multiple independent ways simultaneously makes the case for a systemic problem in our model of early galaxy formation stronger. Each anomaly alone could be explained by a special scenario. All three anomalies together, the age, the mass, the structure, point at something more fundamental. The disk structure observation also connects to a broader pattern that Webb has revealed across its early survey work. A higher fraction of galaxies in the early universe appear to have more organized structures than models predict. Hubble's limitations meant the morphology of very early galaxies was poorly constrained. Webb's resolution has revealed that early galaxies across a range of ages are more disk-like, more structured, and more organized than the simulations that guided galaxy formation research for decades ever suggested. Theorists have proposed several explanations. Some invoke the smooth nature of primordial gas in the early universe, arguing that pristine hydrogen and helium with no heavy elements may collapse into rotating disks more efficiently than enriched gas does. Others suggest that dark matter halos in the early universe may have had different spin properties than later halos, seeding more rotationally organized structures. These are legitimate scientific proposals. They are also unmistakably post hoc. They were developed in response to Webb's observations, not before them. The predictions ran in the opposite direction. The field is in the position of explaining data it failed to predict, which is exactly the position science enters just before a significant theoretical revision takes hold. And the simulations that were supposed to predict this data have their own story to tell, one that reveals the depth of the problem in stark computational terms. Cosmological simulations are among the most computationally intensive projects in science. They run on some of the most powerful supercomputers in the world. Teams spend years developing the physical models they encode, incorporating gravity, gas dynamics, star formation, stellar feedback, black hole growth, magnetic fields, and cosmic expansion into a single framework. They are initialized with conditions matched to the cosmic microwave background measurements and run forward through billions of years of simulated cosmic time. The goal is to reproduce the universe we observe, galaxy by galaxy, cluster by cluster, across the full range of cosmic history. For decades, these simulations performed impressively. The large-scale structure of the universe, the cosmic web of filaments and voids, matched observations. The properties of modern galaxies like size, mass, star formation rates, and chemical composition fell within observed ranges. The distribution of galaxy masses across different cosmic epochs broadly agreed with survey data. The simulations were validated repeatedly, refined with each new dataset, and trusted as a reliable guide to the physics of galaxy formation. Then, Webb's data arrived. The simulations had made specific predictions about what the early universe should look like. The number of massive galaxies at high redshift, meaning galaxies observed when the universe was young, should be vanishingly small. The most massive early galaxies should be far less massive than nearby galaxies today. Their star formation rates should be modest. Their shapes should be irregular. Webb found galaxies that exceed the simulation's predicted mass limits at high redshift by factors of 10 or more in some cases. The star formation rates observed in these ancient galaxies push past the upper bounds the simulations generate. The structural organization of early galaxies is more ordered than the simulations produce. Simulation teams have responded by trying to modify their models. Some increased the efficiency of star formation in early universe conditions. Some adjusted how stellar feedback, the way dying stars push gas outward, and slow further star formation, operates in low metallicity environments, similar to the early universe. Some tweaked the parameters governing black hole growth in the first galaxies. These adjustments help in limited ways. They can bring one property of early galaxies closer to the observed range, while pushing another property further out. The simulations are constrained. Changing one parameter affects everything else simultaneously. Getting the mass right tends to break the star formation rate. Getting the star formation rate right produces galaxies with shapes that still do not match. The inability of current simulations to reproduce Webb's observations is not a minor calibration issue. It points to a genuine gap in the physical models the simulations encode. Something happening in the early universe, some process or combination of processes, is producing galaxies that our best physical models, translated into the most powerful simulations humanity has built, cannot replicate. Identifying what that missing physics is requires a combination of new observations and new theory. Webb is providing the observations faster than the theory is advancing to meet them. The data is outrunning the explanations, which is an uncomfortable position for a mature scientific field to find itself in. But one exotic proposal has started gaining traction in the theoretical community, an idea involving objects so extreme that their very existence in the early universe would rewrite the story of how galaxies were born. Black holes are usually the product of stellar death. A massive star burns through its fuel over millions of years, then collapses under its own gravity. If the remaining core is heavy enough, gravity wins completely, and a black hole forms. This is the standard picture, well supported by observations and consistent with stellar evolution theory. But there is a class of black holes that may have formed through an entirely different process, one that has nothing to do with dying stars. These are called primordial black holes, and if they exist, they formed in the first fractions of a second after the Big Bang, from density fluctuations so extreme that regions of the early universe's plasma collapsed directly into black holes before any stars ever formed. Primordial black holes have never been confirmed. They are a theoretical prediction, and searchers for them have placed constraints on what their masses and abundances could be. But they have not been ruled out across all mass ranges, and certain mass windows remain open. Here is why they matter for the ancient galaxy problem. A supermassive black hole at the center of a galaxy's growth, it acts as a gravitational anchor, pulling in surrounding gas. That gas forms a disk around the black hole, heats to extreme temperatures, and produces enormous amounts of radiation. The radiation drives powerful outflows that push gas outward, but also compresses surrounding gas clouds, triggering bursts of star formation. A supermassive black hole is simultaneously a destroyer and an accelerator, suppressing star formation in some regions while triggering it intensely in others. In the standard picture, supermassive black holes grow slowly alongside their host galaxies. They start as the collapsed cores of massive stars, then grow by consuming gas and merging with other black holes over billions of years. Getting a supermassive black hole in place early enough to drive rapid galaxy formation in the first 300 million years is very difficult within this framework. Primordial black holes offer a shortcut. If black holes with masses already in the supermassive range formed directly from primordial density fluctuations, they would have been in place from the universe's earliest moments. A galaxy forming around a pre-existing supermassive black hole would have had a powerful gravitational and energetic engine at its center from the very beginning. Star formation rates could be dramatically higher. The galaxy could assemble its mass in a fraction of the time a galaxy without such an anchor would need. This is the accelerator theory. A primordial black hole seeds a galaxy that grows far faster than the standard model allows, producing exactly the kind of object Webb has been finding. The theory is scientifically grounded. It does not require any violation of known physics. It requires only that primordial black holes exist in the right mass range, which current observational constraints do not rule out. What makes it compelling as an explanation for Webb's discoveries is that it connects two unsolved problems: the origin of supermassive black holes and the existence of overmassive early galaxies, through a single mechanism. What it requires to move from compelling to confirmed is direct evidence of primordial black holes. And that evidence may be closer than most people expect. The early universe was a place so different from anything that exists today that applying our current understanding of matter to it requires caution. Today, matter behaves in well-understood ways. Gravity pulls it together over time. Gas heated by compression pushes back against collapse. Magnetic fields thread through gas clouds and resist certain types of collapse. Turbulence stirs and disrupts regions that might otherwise condense into stars. These forces balance and compete, and the result is the relatively slow, steady process of galaxy and star formation that we observe in the modern universe. In the first few 100 million years after the Big Bang, the conditions were fundamentally different in ways that may have allowed matter to behave outside those familiar constraints. The universe was denser overall. Gas was pristine, essentially pure hydrogen and helium, with no heavy elements to complicate cooling. The absence of heavy elements matters, because heavy elements play a crucial role in how gas clouds cool. Metal-enriched gas, the kind that fills the interstellar medium of modern galaxies, radiates heat efficiently through a range of atomic and molecular transitions. This efficient cooling allows gas to collapse into relatively small, dense clumps that form stars of modest mass. Primordial gas, lacking those cooling channels, behaves differently. It cools less efficiently and must compress further before it can fragment and ignite as stars. The resulting stars are predicted to be much more massive than modern stars, potentially hundreds of times the mass of the Sun. These are the population 3 stars discussed earlier, never directly observed, but theoretically expected to have existed in the early universe. If population 3 stars were extremely massive, their lives were extremely short and extremely energetic. They would have generated intense ultraviolet radiation that could reionize surrounding gas, ionization fronts that compressed neighboring gas clouds and triggered new star formation. They would have exploded as hypernovae, stellar explosions far more energetic than typical supernovae, dispersing heavy elements across vast distances and seeding enormous volumes of surrounding gas simultaneously. The combination of more massive stars, more energetic deaths, more efficient heavy element dispersal, and more intense radiation fields in early galaxies creates a very different environment for galaxy growth than the one encoded in simulations calibrated to modern galaxy formation physics. The early universe's galaxy-building machinery may have simply run hotter and faster than the machinery that builds galaxies today. This does not require new physics in the sense of overturning known laws. It requires recognizing that the same laws, operating under vastly different initial conditions, can produce qualitatively different outcomes. The challenge for theorists is quantifying exactly how different those outcomes would be, which requires simulating galaxy formation under pristine early universe conditions with enough resolution to capture the behavior of individual population 3 stars. That kind of simulation is only now becoming computationally feasible, and the results being produced are beginning to show that the early universe's galaxy-building potential may have been significantly underestimated, in ways that bring the ancient galaxy's existence from impossible closer to merely extraordinary. The most important stars in the history of the universe have never been seen. Population 3 stars, the first generation, the ones that formed from pure primordial hydrogen and helium left over from the Big Bang, are the missing piece of the cosmic origin story. Every heavy element that exists in every star, every planet, every living cell was manufactured by subsequent generations of stars that came after them. But the very first generation, the stars that started the chain, has never been directly observed. This is partly because they formed so long ago and so far away that their individual light is beyond the reach of any previous telescope. It is also because they are believed to have been extraordinarily short-lived. A star 100 times the mass of the Sun burns through its fuel millions of times faster than the Sun does. Where the Sun will live for roughly 10 billion years, a population 3 star of that mass might live for only 2 to 3 million years. From the perspective of cosmic time, they blazed and vanished almost instantly. What they left behind is the chemical enrichment visible in every subsequent generation of stars. The heavy elements they scattered are a legacy we can measure, even if we cannot see the source. Before Webb, that was the only evidence of their existence, an indirect chemical fingerprint preserved in the composition of old population 2 stars. Webb changed the detection prospects dramatically. Its infrared sensitivity, at the distances corresponding to the first few 100 million years of cosmic history, is sufficient to detect the strongest emission lines produced by population 3 stars if they exist in large enough numbers or in sufficiently luminous clusters. Astronomers have identified several candidate regions in Webb's data where the spectral signatures hint at population 3 star populations. These are preliminary results, not confirmed detections. The signatures that suggest population 3 stars can also be produced by other extreme astrophysical phenomena. Confirming a true population 3, population requires ruling out every alternative explanation, which demands extended observation time and careful analysis. If population 3 stars are directly confirmed by Webb, the implications extend beyond simply checking off the first generation on the stellar census. Their properties, mass distribution, lifetime and energy output, directly constrain models of how quickly the first galaxies could have assembled their stellar mass. A confirmed population 3, population that is more massive and more numerous than current models assume, would go a long way toward explaining how galaxies grew so fast in the early universe. The ancient galaxy that started this conversation may itself contain evidence of population 3 stars buried in its spectral data. The chemical enrichment signatures that suggested a prior stellar generation are consistent with enrichment by extremely massive, short-lived stars. Connecting those signatures directly to population 3, populations would close a gap in the story that has remained open since the first papers on early galaxy formation were published. Webb's ongoing observations are pushing toward that confirmation. Each new target, each new spectrum, adds detail to a picture that is becoming clearer and more troubling in equal measure. And the more clearly humanity can see the earliest stars, the more sharply the question comes into focus: what else was out there in the early universe that we have not yet found? The discovery of one galaxy at 300 million years triggered a race. Astronomers began systematically targeting the regions of Webb's sky survey where the oldest objects were most likely to hide. The logic is straightforward. If one galaxy at 300 million years challenges the model, a galaxy at 200 million years would shatter it. A galaxy at 100 million years would place it firmly inside the Dark Ages, the period when the universe was supposed to be entirely devoid of any luminous structure. Finding such an object would be the single most dramatic astronomical discovery in modern history. It would unambiguously demonstrate that the standard cosmological timeline cannot describe the universe's early chapters without major revision. And based on Webb's track record in its first years of operation, the possibility cannot be dismissed. The technical challenge intensifies with each step further back in time. A galaxy at 100 million years after the Big Bang would have its light stretched even further into the infrared, requiring longer exposure times and more careful analysis to confirm. The signal would be fainter, the redshift would be more extreme, and confirming it spectroscopically would require Webb to stare at the target for extended periods. Webb has a finite operational lifetime. It carries a limited supply of fuel for its orbital station-keeping maneuvers. Unlike Hubble, it cannot be serviced by astronauts. When the fuel runs out, or when an instrument eventually fails, the telescope's scientific life ends. Current estimates place its operational lifetime at 20 years from launch, potentially longer with careful fuel management. That gives astronomers roughly until the early 2040s to extract as much data as possible. The search for the oldest galaxies is therefore operating against a ticking clock. Every month of observing time allocated to other targets is a month not spent probing the edge of the observable universe's earliest structures. Committees that allocate Webb's observing time face genuine scientific trade-offs, balancing the urgent search for ancient galaxies against the hundreds of other extraordinary science cases the telescope was built to address. Several programs have been dedicated specifically to searching for extremely high redshift galaxy candidates. They cast wide nets across large portions of Webb's accessible sky, identifying objects whose light profiles suggest extreme distances. Candidates are then flagged for spectroscopic follow-up, the more time-intensive measurement that confirms the redshift and rules out alternatives. Each confirmed detection pushes the observational boundary further. Each new limit established, even without a detection, tells theorists something about what the early universe contained. An absence of galaxies at a certain age and mass is also information. It constrains models from below as well as above. Astronomers working on these programs describe the atmosphere as similar to the early days of a major exploration era. The map is being drawn in real time. The territory keeps delivering surprises, and every new confirmed object at the edge of observable time carries the possibility of being the one that finally forces the question that cannot be deferred any longer. How old is the universe really, and what was it doing in its very first moments? There is a specific kind of moment in science when an instrument shows you something your entire theoretical framework says cannot be there. It is different from finding something unexpected. Unexpected discoveries happen constantly. A new type of particle, a previously unobserved phenomenon, a process that was theoretically possible but had never been confirmed. Those discoveries expand the map without challenging its borders. Finding something that violates a model's explicit prediction is categorically different. The feeling is not celebration. It is the slow, uncomfortable recognition that something you built your work on has a problem. The researchers who confirmed the ancient galaxy described this exact experience. Years of work in the field meant years of internalized assumptions about when and how galaxies could form. The timeline was not just an abstract fact to be looked up. It was embedded in every calculation, every prediction, every data analysis. Seeing an object that violated it was not like finding a new country on an already complete map. It was like finding that the ocean is in the wrong place. For the public, discoveries that challenge models tend to generate excitement. For scientists who built on those models, the reaction is more complicated. A wrong assumption in a foundational model can invalidate not just one paper, but entire research programs built on that foundation. It means revisiting conclusions. It means asking which results that seemed solid were actually contingent on the assumption that has now been questioned. The ancient galaxy has produced exactly this kind of reverberating uncertainty. Researchers working on early galaxy formation surveys have begun the tedious but necessary process of asking which of their previous results depend on the assumption that no massive galaxies existed before a certain age. Some will survive the revision, others may not. This is healthy. Science advances through exactly this kind of disruption. The history of cosmology is a history of comfortable models being punctured by inconvenient observations, revised and rebuilt stronger. The cosmic microwave background itself was an observation that required theoretical revision. Dark matter was proposed to explain something the then current model could not account for. Dark energy emerged from data that forced a rethinking of the universe's fate. Each revision was painful in the short term and productive over the long term. The ancient galaxy is following the same path. The discomfort it produced in the scientific community is evidence that it hit something real, a genuine fault line in the current framework that could not be papered over with minor adjustments. What makes this moment different from previous revisions is its potential scope. Dark matter and dark energy modified the contents of the model while leaving its timeline intact. The ancient galaxy, and the growing family of objects like it Webb has found, challenges the timeline itself, and a timeline that is wrong in its early chapters forces a question about everything that follows. For humanity, the stakes of this question extend beyond academic cosmology. Our understanding of where we came from, how the structures that gave rise to stars, planets, and life assembled themselves, rests on that timeline. Getting the timeline right matters for the same reason getting any origin story right matters. It is the foundation on which everything else is built. The ancient galaxy contained stars, massive stars, stars with heavy elements. Heavy elements are the building blocks of planets. Carbon, oxygen, silicon, iron, the periodic table of materials that rocky worlds are made of, all require stellar manufacturing. The standard timeline assumed that the first potentially planet-forming stellar chemistry would not exist until well into the universe's second billion years, after enough generations of stars had lived and died to enrich the cosmic gas supply. The ancient galaxy challenges that assumption directly. If stellar populations with heavy elements existed 300 million years after the Big Bang, the raw materials for planetary formation were available far earlier than the standard timeline permits. Planets could theoretically have formed in the first billion years of the universe. And planets, given enough time, can give rise to complexity. A civilization that began developing 300 million years after the Big Bang, in a galaxy like the one Webb found, would have a 13 billion year head start on humanity. The oldest confirmed signals of modern human civilization extend back perhaps 12,000 years. The oldest single-celled life on Earth is roughly 3.5 billion years old. A civilization 13 billion years ahead of us occupies a gap so large it resists meaningful comparison. This is a thought experiment, not a scientific claim. Scientists cannot currently confirm whether any planets formed in the ancient galaxy, whether those planets had stable orbits and liquid water, or whether any form of life emerged on them. The chain of inferences required to get from heavy elements present to civilization possible is long, and each link is uncertain. But the thought experiment is scientifically grounded in a way it was not before Webb's discovery. Before confirming that heavy elements existed in the early universe, the possibility of early universe civilizations was purely speculative, with no observational anchor. Now there is an anchor, a confirmed galaxy with enriched stellar populations at an age the standard model said was impossible for such chemistry to exist. Astrobiologists have begun incorporating early universe galaxy formation data into their models of the cosmic habitable timeline, the window of cosmic history during which the conditions for life can plausibly exist. If the window opens earlier than previously assumed, the statistical landscape for life in the universe changes. More time means more chances. More chances means the universe may be, from a biological perspective, older and more populated, with the prerequisites for complexity than we calculated. The ancient galaxy does not prove life existed 13 billion years ago. It does prove that the universe was building the ingredients earlier than our models allowed. And that proof, quiet and contained in a single set of spectral data, expands the imaginable possibilities of what the cosmos may have produced across its full history. The answer to what those possibilities led to may be waiting for us in light that has not yet reached our instruments. And the telescope doing the looking has a deadline approaching faster than most people realize. The James Webb Space Telescope launched on December 25, 2021, tucked inside an Ariane 5 rocket, and traveled to its orbit 1 million miles from Earth. The launch went nearly perfectly, so precisely did the rocket place Webb on its trajectory that the telescope used far less fuel than the maximum budgeted for orbit insertion. That fuel saving extended the telescope's projected operational lifetime. Original estimates had been cautious, predicting around 10 years of science operations. The revised estimate moved toward 20 years, possibly more, if the remaining systems hold. 20 years sounds comfortable. Scientists know better. Space telescopes do not fail on schedule. They fail when a mirror segment loses its calibration beyond the correction system's ability to compensate. When a detector degrades. When cosmic rays accumulate enough damage in sensitive electronics that signal noise rises above usable thresholds. When the cryocooler that keeps the mid-infrared instrument at near absolute zero loses efficiency. When fuel for station keeping runs out and the telescope can no longer maintain its precise orientation. Any of these could happen before the 20-year mark. Some combination of them certainly will. The teams operating Webb are aware of this, which is why observing time is allocated with such care. Every hour spent on one target is an hour not spent on another. The triage is constant. The programs searching for ancient galaxies at the edge of the observable universe are competing for time with programs studying exoplanet atmospheres, nearby stellar nurseries, galaxy evolution across cosmic time, dark matter distribution, and dozens of other extraordinary science cases. Webb was never designed to do only one thing. It was designed to transform multiple fields simultaneously. The ancient galaxy problem is one thread in a scientific tapestry being woven against a deadline. There is also a second generation to consider. Future space telescopes with capabilities beyond Webb's are in development. The Nancy Grace Roman Space Telescope, a wide-field infrared observatory, is planned to launch in the coming years and will survey the sky at infrared wavelengths with an enormously larger field of view than Webb. The proposed large UV optical infrared surveyor, a future flagship telescope concept, would surpass Webb's sensitivity across a broader range of wavelengths. And concepts for extremely large space-based infrared observatories have been discussed for the post-Webb era. But none of these future telescopes are the James Webb Space Telescope. Webb's specific combination of mirror size, infrared sensitivity, and thermal stability was designed for exactly the observations that have been making headlines. Its successors will extend the reach, not replace the need for the data already being gathered. Every new ancient galaxy Webb confirms before its operational life ends narrows the range of possible explanations for what the early universe did. Every spectrum collected tightens the constraints on the models being proposed to account for the discoveries. The telescope is in a race with its own mortality, and the scientists operating it know it. The data it gathers in the coming years may be the most cosmologically significant ever collected, and what humanity ultimately does with it will define the next chapter of our understanding of existence itself. A discovery that rewrites the origin story of the universe does not produce a clean, immediate revision. It produces a period of contested models, competing interpretations, extraordinary papers, intense arguments, and gradual accumulation of evidence pointing in a single direction. That period can last a decade, sometimes two. The history of cosmology is full of examples where the evidence arrived years before the consensus formed to accept it. The expansion of the universe was measured by Edwin Hubble in the 1920s. The theoretical framework to interpret it, and the recognition that it implied a hot, dense origin, took decades to solidify into what we now call the Big Bang Theory. The cosmic microwave background radiation was discovered accidentally in the 1960s. Its full significance for confirming the Big Bang took additional years of work to establish. Dark energy was inferred from supernova data in 1998. 2 decades later, its nature remains entirely unknown. The ancient galaxy that Webb found is currently in the early stage of that process. The discovery is confirmed. The challenge it presents to the standard model is accepted by the community as real. The explanation remains open. Multiple competing frameworks are being developed simultaneously, each with proponents and critics, each explaining some aspects of the data while struggling with others. This is the correct scientific response. The pressure to produce a tidy, unified explanation immediately is a cultural impulse, not a scientific one. The universe does not owe us answers on a convenient timeline. What it offers is data, and Webb is delivering data at a pace that the theoretical community is genuinely working to match. What is already clear from the convergence of the ancient galaxy discoveries, the Hubble tension, the simulation failures, and the growing family of early universe anomalies Webb has uncovered, is that the standard cosmological model has reached a boundary. It remains the best description of the universe across most of its history. It remains the foundation of the field, but its description of the universe's earliest chapters contains something that is either wrong, incomplete, or pointing toward physics that has not yet been incorporated. That something is now confirmed observationally. It has a face. It is a galaxy, blazing with billions of stars, existing in a universe 300 million years old, in a place and at a time the standard model reserved for darkness and the slow beginning of structure. Finding it required building the most sophisticated observatory in human history and pointing it at the oldest corners of the universe. Understanding it will require theoretical breakthroughs that may take a generation of physicists to develop, and applying that understanding will likely transform how humanity describes its own origin, which is ultimately what cosmology is about. The universe's story did not begin the way we wrote it, and rewriting it is not a failure. It is the whole point. Every major advance in humanity's understanding of the cosmos began with an observation that did not fit. The orbit of Mercury did not fit Newtonian gravity. Einstein's general relativity explained it and changed physics forever. The brightness of distant supernovae did not fit a universe decelerating under gravity. Dark energy was the answer, and cosmology absorbed a new component it had not known existed. The flat rotation curves of galaxies did not fit the visible matter inside them. Dark matter became a cornerstone of the standard model. In each case, the anomaly preceded the explanation by years or decades. In each case, the temptation to explain away the anomaly, to find an observational error or a special case excuse, gave way eventually to accepting that the universe was showing us something real that our current framework could not account for. The ancient galaxy Webb found is the latest entry in this tradition. It is the anomaly that is now real, confirmed, and demanding an explanation the community does not yet have. And it is not alone. Webb has found multiple galaxies pushing against the standard timeline in its first years of operation. Galaxies that are collectively too massive, too bright, too structured, and too chemically enriched to fit the universe we thought we understood. What humanity does with this discovery, and with the family of similar objects accumulating in Webb's data, is the same thing it has always done. It looks harder, it measures more carefully, it builds better models, tests them against new data, discards what fails, and keeps what survives. The James Webb Space Telescope represents the current peak of that process. Its remaining operational years will produce observations that future generations of physicists will spend careers analyzing. The ancient galaxy's discovery has already redirected funding toward early universe observations, pushed theorists to revisit shelved ideas, and inspired proposals for next-generation instruments with even greater reach. The question of what the early universe actually looked like is no longer purely theoretical. Webb has made it observational. The answer is being assembled, piece by confirmed piece, galaxy by ancient galaxy, from light that has been traveling toward our instruments for over 13 billion years. Somewhere in the deep infrared, in wavelengths invisible to human eyes, but perfectly legible to the mirror Webb has positioned at the edge of our cosmic neighborhood. There may already be an even older galaxy waiting in the data. Something more extreme. Something that pushes the question further. Something that the current models cannot accommodate at all. Scientists are looking. The mirror is cold, the detectors are running, and the universe is sending its oldest light toward the one instrument we have built capable of receiving it. The story of the universe's beginning is being rewritten. The authors are galaxies that formed before the laws we wrote for them permitted, and the telescope reading their light back to us is, by any honest reckoning, the most extraordinary machine humanity has ever launched into the dark. We thought we understood the first chapter. We were wrong. And being wrong, in the hands of the right instruments and the right minds, is the beginning of every discovery that has ever mattered.